Stock and option trading has been practiced for hundreds of years and was largely an opinion-based career. It was only in the 70s, however, when more academics started getting involved in trying to provide mathematical models for how to price stocks and options. Many of these academics were successful and made large sums of money with these models. We are going to consider a particularly famous model for pricing European options called the Black-Scholes formula, which received the Nobel Prize in Economics in 1997. In order to understand Black-Scholes, you need to understand three key mathematical concepts: martingales, Brownian motion, and stochastic calculus. We are going to consider these three mathematical concepts throughout the video, finishing with the Black-Scholes formula. Let's first consider the simple example of a horse race. So suppose you're a bookie trying to determine the odds you should give for a simple horse race. The race consists of two horses, A and B, where there is currently 5,000 bet on A and 10,000 bet on B. Looking at the payouts, we will see that if horse A wins, we'll have to pay out 50,000 times the odds of A, and we will receive 10,000. And if horse B wins, we have to pay out 10,000 times the odds of B, and we're going to receive 50,000. The problem is, we don't know the odds of either. So, what we are going to do is go to an expert advisor who knows all about the horses and ask him. He thinks that there's a 20% chance of A winning and an 80% chance of B winning. Now, with a quick revision of probability, we can calculate the odds as being 1 to 4 for A and 4 to 1 for B. Subbing these values in, we will see that if horse A wins, we will get a total profit of negative 2,500, and if horse B wins, we will receive 10,000. So, we now consider the expected value. According to these probabilities, if they are correct, our expected value will be the sum of our profit times the probability. This will leave us with an expected value of 0. Now this is assuming that our expert advisor got the probability right. But what if our expert advisor got the probability wrong? What if it was, say, 90% chance that horse A wins and 10% chance that horse B wins? This would leave us with a negative. The way we get around this is by using something called risk-neutral pricing. So what we are going to do is adjust our probabilities according to the market. And according to the market, there is a probability of 16.67% of horse B and 83.33% for horse A. This gives us odds of 1 to 5 for A and 5 to 1 for B. Now, subbing these values in, we will see that we will always have a value of 0. This means that no matter the probability, we will always get an expected value of 0, which is what we want. In this simple example, we have actually considered many important topics in probability. First of all, we have a random variable. This was which horse will win the race. We could have also considered how many strides the horse takes or if a horse will fall, but the random variable we chose is which horse will win. Then on this random variable we defined different probability distributions. We had the expert advisor probability distribution, we had the actual one, and we had the risk-neutral probability distribution. Finally, we considered the expected values and how the expected value changes if the expert advisor doesn't get his probabilities correct, and how if we use the risk-neutral probability, then the expected value will always be 0. This risk-neutral pricing framework is exactly what we are going to use to value our options. So let's consider a one-period binomial model. In this model, we will have a stock which starts at 4 times 0 and can move to 8 with probability P, or 2 with probability Q at time 1. We will use U and D to denote if the stock price went up or down at time 1, and we will also have a risk-free rate of interest or. So our current model looks like this. It can either go up U or down D. Again, in this model, we are not making any assumptions on the probability. We do not need to, as we have just seen with the risk-neutral pricing framework. The only difference here is that in this model, we will also have a risk-free rate of interest, or. This will make a difference. Now that we have our one-step binomial model laid out, we are going to consider functions of stock prices. This is all a derivative is. A derivative is simply a function of the stock price. So, for example, if our function is x squared, and if our stock price at time 1 is 10, then the value of a derivative will be 10 squared. Some derivatives have special names, such as a call option, which has the following payout function: the max of x minus k and 0. K is typically called the strike price. Let's consider this call option with a strike price of 5 on our current model. So, we want to know what the value of the call option at time 0, but we do not know that. However, we do know the stock price at time 1. So subbing this in to the value of our call option, we will be able to get the specific values for up and down of our call option. Before we try to figure out the value of our call option at time 0, we are going to consider an important assumption. This assumption is called the no arbitrage principle, and it isn't that crazy of an assumption. What it says is that you cannot have a trading strategy that begins with no money, has 0 probability of losing money, and has a positive probability of making money. What this basically means is that you can't make profit risk-free. So if we look at our current model, you can even see the no arbitrage principle in this. Our stock starts at 4 and it can go to 8 or 2. It can't go above the risk-free rate without a chance of going below it as well. Alright, with that assumption in mind, we're going to look at our current model. Using our call option with strike price 5, we were able to figure out the value of the call option at time 1. And what we are trying to figure out is the value of the call option at time 0. Now, as a consequence of the no arbitrage principle, if 2 portfolios have the same payoffs at every time, then they must have the same value at time 0. This is what we are going to use to value our call option. We are going to create a portfolio of the stock and bond which has the same payoffs as our call option, and then at time 0 these portfolios will have to be equal. So let's consider our portfolio strategy. We start off with an amount x0 and we start out an amount delta naught of stock. So our portfolio at time 0 x0 is some amount of stock and then some amount of bond, which is x0 minus delta naught s0. We then see how this changes at time 1, and what we want is this to equal the value of our call options. Now we sub in our values that we already have, and we will get these equations. Now if you look at the bottom 2 equations, we can solve these. What you will see is there are 2 equations and 2 unknowns, which you'll be able to solve to get x0 equals 1.2. Now from above, you will see that we created our portfolio so that it was equal to the call option. So this will also be equal to 1.2. This is the way you value a call option by replicating a portfolio. Previously, we found the value of a call option with strike price 5 by replicating the portfolio. We now consider an alternative approach. So, in our horse example, we had a sort of theoretically implied probability, which we called the risk-neutral probability, which made it so our profit was always 0. We want to do something similar for our simple stock model. The only difference is that we will also have a risk-free rate of interest. So instead of it equaling 0, we will actually equal the risk-free rate. So let's take a look at our current model. Currently, we have a stock which at time 0 is at 4, and it can go to 8 or 2. We're going to pretend we don't know the call option's price at time 0, but what we will be seeing previously is the call option at time 1, either with 3 or 0. What we do then is we say that the risk-neutral expectation of our stock is equal to the stock value at time 0 times the risk-free rate. So what you have to think of here is what probabilities would we have to have so that our stock would be the same as our risk-free rate on expectation. Now these are not the actual probabilities. The actual probabilities will be much different. However, these are the ones that will make our stock the same as our risk-free rate. So let's expand this a bit. And now if we notice that Q, which is 1 minus P, we can expand it further. And we sub in our values, and we can actually calculate the values of these probabilities. We will get P and Q equal to 1/2. And it is really important to remember these aren't the actual probabilities. These are these sort of made up probabilities that we have made so that our risk-free is the exact same as our stock. Now what is really interesting is we can actually do the exact same for a call option, and because the call option is just a function of our stock, that is all it takes in is our stock. These probabilities will be the exact same. So we will get something like this. Our risk-free rate times their initial call option will be equal to the risk-neutral expectation of our call option at time 1. Now, if you notice this time, we actually know the values of P and Q, we just got them, but we don't know the value of our call option at time 0. So what we can then do is sub in these values and finally get the value of the call option the same as the same value as we got with the replicating portfolio way. This concept is really important, and it is the exact way we are going to derive Black-Scholes. The only difference being we're going to have a more complicated stock graph. So what we did is we calculated the probabilities from our stock, setting the expected value of the stock equal to the risk-free rate. We then use this to get the value of our call option at time 0 as the risk-free probabilities to sale. Now, we are going to call this our risk-neutral pricing formula, as shown in the yellow box. So, the value of any option whose payoffs is just at the end, so just like a European call option, we will actually get is the value at time n. So we just considered the value at time 0 and 1, but this is more general than that. What it says is the value at time n is equal to the risk-neutral expectation, and we've just brought over the risk-free rate 1 plus or, so it's equal to the value of the option at time n plus 1 discounted. We call this a risk-neutral martingale. So this is no different to what we just did. We have a value of some option at time n plus 1. Now instead of saying that our option is accumulated 1 plus 4, we're just going to discount it. So it's the value of our option n plus 1 discounted. We then get the risk-neutral expectation, and we're saying that is equal to the value of the option at time n. So we have our risk-neutral framework, which is exactly what we're going to use to derive Black-Scholes, but one small problem. Let's take a look at our current stock model. Currently our stock model says 2 times 0, 1 can go up or it can go down. This is alright, but it is really not the best, because if we look at current stock prices, they are much more volatile. They can go up and down a lot more and are much more jaggedy. So if we want the value of our call option at time 0 to be accurate, we're going to need a much more realistic model for our stock. This is what we are going to consider in the next section of this video. In order to model our stock price better, we are first going to consider a simple random walk. So, we create a simple random walk by tossing a coin repeatedly. We will then define as heads is +1 and tails is -1. Finally, we consider the pass that the sum of these coin tosses makes as time increases. So, we have a sequence of events, W1 to W10. We then define a random variable, x1 to x10 for each of these. And now we toss our coin, and we assign a value +1 to -1, and we graph the sum of these. That is all our simple random walk is. You can see that these paths are much more jaggedy than our simple one-step pattern. They can go up and down a lot more and kind of look like the stock prices we previously considered. So again, all we're doing is flipping a coin, giving the value +1 to heads, -1 to tails, and summing over these events. So let's consider the last one with that sort of motion. Now, simple random walk has some very interesting properties that we would like to consider. So, the first property is that the simple random walk has independent increments. This is really easy to see. If you consider, say, 4 to 5, all that this is dependent on is just a single coin toss, so it can either be head or tail. So obviously this increment will be independent of the other ones. The next one, which you might have seen me put up on the last slide, is the martingale property. Now what the martingale property says is that given the information up to a certain time, that's what fk means, the expected value will just be the current value. Now let's think about this a bit more. So say we're at the value 4. We can either go up +1, the probability half, or down -1, the probability half. So what would our expected value be? Well, it would just be the value we're at currently, which would be 4. And we can actually continue this on to any 2 points on our simple random walk. So for example, if we're at point 4, and we want to know what the expected value at 8 will be, it will just be the value at 4. Our simple random walk still does not really look like a stock price. So in order to get it to look like a stock price, we are going to speed up time and scale down the step size of a simple random walk. This is called a scaled random walk and is defined below, where n sub nt is simply just a simple random walk with nt time steps. Let's take a look at what this looks like. So we have our event, which now is a sequence of 50 heads or tails, each which instead of having a random variable +1 or -1, have a value of -0.1 or +1.1. Looking at the graph, it is much more like a stock price and has some very interesting properties. If we consider all possible paths, remembering the green path is just one particular path that the scale random walk can take. So the blue triangle is all possible paths. It is actually approximately normally distributed. And as we let n go into infinity, this will become more exact. We have previously seen that as n goes to infinity, our scale random walk becomes approximately normal. What if just approximately normal we consider a process that is exactly normal at every time step? This is what a Brownian motion is. Its path looks like this. As we can see, this looks very like a stock price. So let's consider some properties of the Brownian motion. First of all, a Brownian motion at time 0 is equal to 0. Then, for each increment, just like the simple random walk, they are independent of each other. And just like the scale random walk as n goes to infinity, they are normally distributed. Next, we are going to consider the expected value of these increments. Their expected values are 0 and their variance is the increment size. Now, a Brownian motion also has the martingale property. That means that at any time, if we look at the expected value of the stock price, it is just going to be the current value. The only difference here is that now our S and T are continuous. So instead of increments, it can be any value at all. Brownian motion is an okay model for stock prices. However, we need to adjust for two things. Firstly, we don't really want the stock to start at price 0, as in reality, that's not the case. And secondly, we want a trend line that is at least a risk-free rate. Otherwise, there would be no point in investing in stocks. We now consider a geometric Brownian motion. So firstly, a Brownian motion is shown, and then a geometric Brownian motion, which is shifted up and has a nice trend line, which is much more like the actual path of the stock price. A geometric Brownian motion is defined by a stochastic differential equation. This may seem complicated, but all it is our trend line, mu x of t dt, and our Brownian motion, sigma d omega t. Solving this, we get the following. This is all the desirable properties we want. The exponential allows us to have a stock price that doesn't start at 0. The coefficient of t allows us to have a trend line, and the Brownian motion, omega t, allows us to have the jaggedy path we want. So, properties of a geometric Brownian motion. Geometric Brownian motion is log-normally distributed and has the following expected value and variances. This is a stock price we will use for Black-Scholes. However, there is one small problem. In our previous model, we valued derivatives by getting functions of the stock price, so we will need to be able to do the same for geometric Brownian motion. We will also need to be able to get the differential of this function. As geometric Brownian motion is in continuous time, so our portfolio will have to be the same at every time on a continuous line instead of just the single time steps. In order to derive Black-Scholes, we will need to be able to get differentials of functions of geometric Brownian motion. This is where stochastic calculus comes in. In ordinary calculus, we just use deterministic normal variables, whereas in stochastic calculus, we use random variables. This has some important consequences, as we will now see. For traditional calculus, we are simply able to get the derivative as the limit of the slope. This allows us to define a tangent line to the curve as the derivative, and means as the difference in points becomes close in regards to the t-axis, so do they on the f-t axis. This does not work in geometric Brownian motion, as we will now see. See, geometric Brownian motion has an extra randomness to it. This means that no matter how far we zoom in and how far we make our points close together, there will always be some difference due to the randomness. How do we quantify the randomness that leads to a difference between traditional calculus and this new stochastic calculus? We use a thing called quadratic variation. What quadratic variation does is divide your t-axis into a number of intervals. It takes the difference between the value of your stochastic process or function at each interval point and squares them. It then sums over all of these differences and finally makes the original interval smaller and smaller and smaller. So again, we take the difference in the values of our stochastic process, which will be small, then we square them, which will make them even smaller, and finally we will sum over all of these small things. For a normal continuous function which has a continuous derivative, the quadratic variation is 0. Thinking back to the previous example, it makes sense, because we see, as we made our t smaller and smaller and smaller, our f of t became smaller and smaller and smaller as well. But now the square of a small thing is even smaller. So in totality, we will have the sum of a lot of things that will go to 0, which will leave us with a value of 0. However, for quadratic variation, this will be different. As in the previous example, we see how as we made t smaller and smaller and smaller, the randomness in the random variables made it so that the values of our stochastic process did not become as small as the t. This means that as we square them, there will still be a small bit left over. And as we sum over all of these, we will get the value t. This is a really important concept and is the reason stochastic calculus is different to ordinary calculus. We say that Brownian motion accumulates quadratic variation at a rate of 1 per unit time, and informally write it as the product of two differentials. We can consider the sum of a Brownian motion times by a normal one, and this will be 0 along with the normal quadratic variation of a normal function, which will also be 0. The relations at the bottom are important and make stochastic calculus easier to use. Now that we have a quantitative measure for the difference between Brownian motion and normal functions, we're going to try and figure out what the differential of a function in Brownian motion is. What is important to note is that we are not taking the derivative of Brownian motion, or we're not taking the differential of Brownian motion. What we are doing is getting a function, summing in 2 points of Brownian motion that are close together, and then getting the difference between them. In order to do this, let's have a quick revision of Taylor's formula. Taylor's formula approximates a function at a point as a series of its derivatives. If we sub in our infinitesimal distance dx and move 1 to the other side, we are going to get the formula for a differential of a function of x as follows. Now, as we've seen for traditional calculus, this dx squared term and the x cubed term will both go to 0, as they have a quadratic variation of 0. Continuing this down, we get the differential of a function of x as follows. If instead of using a normal variable, we now use a Brownian motion variable, we will see the following. All we have done is sub in the differential of our Brownian motion instead of the differential of our normal random variable x. And if we remember from the previous slides, the quadratic variation of a Brownian motion is not 0. So simplifying this further, we get the following formula. Now, we call this formula its simple version. And are going to expand this for a general geometric Brownian motion and a function of 2 variables. So now continuing on to the differential of a function of 2 variables, t and s of t, where s of t is our geometric Brownian motion. Now, we need to remember how our geometric Brownian motion was defined as a stochastic differential equation. We defined it as d of s of t equals mu st dt plus sigma d omega t. Now, in a kind of informal way, we can write the quadratic variation as follows. This would be very useful for simplifying our general Taylor's formula, just like we did in the previous example. But first, let's consider the Taylor's formula for 2 variables. So, It is quite similar to the Taylor's formula for one variable, except in this one we are going to use partial derivatives, but otherwise it is the same. It is just a sequence of derivatives of the function we want to consider. We then simplify this just to the same, and we get the following formula. We are now going to sub in our geometric Brownian motion and simplify. If you remember previously, the dt squared and the dst dt quadratic variations were both 0, so both these terms go to 0. Then, looking at how our geometric Brownian motion was defined, and using the kind of informal quadratic variation, we can sub these values in to get the following formula. And finally, with a few simplifications, we get the following. This is the differential of a function of two variables, one normal variable and one geometric Brownian motion variable. This is really important in the Black-Scholes formula. Finally, we have all the tools needed to derive Black-Scholes. So let's consider our current model. So currently we have a stock which is modeled by geometric Brownian motion. dst equals mu st dt equals sigma d omega t, and we have a risk-free rate of interest. What our goal is then is to try and find the value of a call option at time 0. Now our call option has the following payoff function, which we had seen previously. So let's remember in the one-step binomial model, we had two methods for getting the value of our call option. We had a replicating portfolio weight and a risk-neutral expectation weight. So the way we are actually going to use is the risk-neutral expectation weight. But before we do that, we're going to take a quick look at the replicating portfolio. So, for our replicating portfolio weight, we're going to have a portfolio x of t, which is made up of some amount of the stock, delta t, and we're going to have the remainder in the risk-free asset. So this can actually be positive or negative, the risk-free asset, because you can think of it as saving in the bank or borrowing from the bank. Then, just like how we had the value of the portfolio equal the value of the call option at each time, because we are in continuous time, we're going to use a differential of the portfolio. So what we are going to say is the change in the portfolio is going to equal the change in the call option at every time. And if both of the changes are the same, and they have the same initial value, then they should match up perfectly, and we should be able to get the call option price as just the initial value of the portfolio. So, let's now consider the differential of the call option. We actually have to use Ito-Dubin's formula for this because we're considering a function of a stochastic process. So if we expand it, we get this. And if we do a few substitutions, we'll finally get this, subbing in our values for geometric Brownian motion. There it is. Now, before we let them equal each other, we are actually going to do one small thing. We are going to get the discounted value of d. And again, to get the next stage, we're going to have to use Ito-Dubin on both of these. So, we're going to have to do more derivations. And finally, if you equate these two and solve, you're going to get the following partial differential equation with the following terminal condition. As we can see, this process has been quite long, and what we end up with is a partial differential equation, which isn't actually the easiest to solve. So that is why we're actually not going to derive it this way, as to solve that will take some time. The way we are going to solve it is through the risk-neutral expectation, which I'll show you now. Let's now consider the risk-neutral Merton go away. So, previously when we were getting the risk-neutral Merton go away, we had a stock price which went up with probability P and down with probability Q. Now we are going to use a stock price which is modeled by geometric Brownian motion. So our geometric Brownian motion is d of s of t equals mu st dt equals sigma s of t d omega t. When we were considering the simple binomial case, what we did was we set our risk-neutral expectation equal to the value of the stock times 0 multiplied by the risk-free rate. So we're essentially making our stock price on average equal the risk-free rate. And what we did from then is, remember, we could get the P and the Q, and then subbing these back in to the call option, we could then calculate the call option at time 0. For the geometric Brownian motion, this is going to be a bit harder. See, with the geometric Brownian motion, we don't have an explicit P and Q. Instead, if we remember from earlier, that our Brownian motion increments are normally distributed. So if we consider the whole increment, this will also be normally distributed. So instead of our stock price taking specific values at the end time, it will actually be on a normal distribution. So it can take any value, and it will have different probabilities according to the normal distribution. Then we also have this new drift term, mu S of t. And what this is just going to do is just going to shift it up or down. So it's going to make our stock prices more likely to be higher if mu is high, and more likely to be low if mu is low. What we want to do is set our mu equal to our R, because mu is our average, the average value of our stock basically. So what we're going to do is set this equal to the risk-free rate, and then on average, just like the binomial case, the risk-neutral expectation will be equal to the initial rate, the initial stock price times R. This is all a bit kind of handy, and to make it more rigorous, we're going to have to use a theorem called Grisano's theorem, and we're going to have to use a bit more calculation to show that the Brownian motion omega q, which is a Brownian motion under this new risk-neutral measure, is actually a valid Brownian motion. But we're just going to skip over these points. So let's finally divide Black-Scholes. So we have a European call option with formula as follows, and we want the price at time 0. We consider the risk-neutral expectation of the discounted value of our call option at time t. This e to the minus rt, that is just equivalent to the 1 over 1 plus r in our unstuck binomial case. The only reason we're using it is because we're in continuous time now, and that is better for the continuous model. Then, just continuing on, we're going to sub in our value for the call option is the max of s of t minus k to 0. Then, we are going to change this max of s of t minus k to an indicator function times s of t minus k. Now, what this indicator function says is that if s of t minus k is greater than 0, it will be a value 1. And if s of t minus k is less than 0, it will be a value 0. This is exactly the same as the max of s of t minus k is 0. Because if we think if s of t minus k is less than 0, then the max is just going to be 0. And if it's greater, it's just going to be s of t minus k. So that's why we're using the indicator function. It just makes our calculation easier to compute. So let's continue our computation. So what we're going to do now is just use a bit of theory about expected values to separate out these two, as they're not dependent on each other. Then we're going to take out our e to the minus rt, which is fairly common. And these are the expected values we want to compute. So the one on the left is a bit more complicated than the one on the right, so we're going to start with the one on the left. The expected value of the indicator function. Well, if we just rearrange our indicator function a bit, it says that if s of t is greater than k, so if our stock price is greater than our strike price, then it will be 1, and if it's less than 0, s of t is less than k, it will be 0. So an expected value is just a probability times the value of the function. So we're just going to have the probability times 1 and the probability times 0. Now this is actually just the probability s of t is greater than k, because we're going to get the values of 1 and we're going to sum them all up times the probability for s of t greater than k, and we're going to get 0 for s of t less than k. Then if we just sub in our value for s of t, we're going to get the following equation. So that's just our geometric Brownian motion under a risk-neutral measure. Then we're going to rearrange it a bit, and we're going to get the following term. All we have done here is we just rearranged the k and all them so that we have what we want on the left and the right hand side. And if you look at our risk-neutral Brownian motion, weighted q of t over root t, well, our Brownian motion over an increment is normally distributed. So this is actually just normally distributed. So if we consider this, it's actually just the normally distributed value of dt, where d2 is just all the values we have simplified them together. So that is how we calculate the right hand side of our above equation. We are now going to consider how to do the left hand side on the next page. So this is what we currently have. We're now going to consider the left hand side. So this is the expected value under the risk-neutral measure of s of t times the indicator function. Remember in the previous one, we just had the indicator function, now we have s of t times the indicator function. So what we're first going to do is we're actually going to bring the e to the minus rt back inside the expected value, and we get the following. Now, this is where it gets a bit more tricky. So we're going to define something called the Radon negative derivative, and you don't really need to know the details of this, but basically, just like how we shifted from the actual probabilities to the risk-neutral probabilities, we're now going to switch to some other probability, and this doesn't really have a meaning, but it just helps us solve the expected value problem. So what we're going to need is the expected value under the risk-neutral measure of some L of t times x, and then in this other new one, which we call p, this new probability measure, that is just going to be the expected value of x. So let's see how this is kind of done. So first of all, we're going to times the outside by s0, and we're also going to divide. So that's just like multiplying by 1. Then we are going to let s of t over s0 times e to the minus rt. We're going to let that equals L of t. And when you kind of work this out, which I haven't shown here, what you will get is that the risk-neutral Brownian motion equals sigma t plus the Brownian motion in this new probability measure. Now there's a lot more to this, and it's a lot more rigorous, but for saving time, we're just going to skip over that part and just accept that the risk-neutral Brownian motion equals sigma t plus the Brownian motion of the new probability measure. Now, using the formula above, continuing on, we're going to just let this equal to the expected value under this new probability measure of the indicator function. That is like our x in the formula up to the right. And we already know how to do this. We just did it for the other case, which was the simpler one. It's just the expected value of the indicator function, which is just the probability. And then we're going to use st as a bit different now. This is one implication that changing the probability measure has. So just like how we changed from geometric Brownian motion to our risk-neutral Brownian motion, we had seen that it changed the mu changed to an r. Kind of similar for this. Now our stock model is a bit different. Instead of having wq of t, we have wp of t, and instead of having r minus 1/2 sigma squared, we're having r plus 1/2 sigma squared. So that's just kind of what happens. You can prove this, but I haven't shown it here. So then, what we have set that as to the normal distribution, just like we've done previously, and we've put all the terms in together to get the following for D1, which may seem all a bit magic, but it is quite simple. All you do is just plug in your value for s of t that we have seen above, and then rearrange to get wq of t over root t, and then that's your normal distribution, and then you just let whatever's on the right hand side equal to D1. So that's what we have. And now we are finally able to consider the full Black-Scholes model for a European call option as follows. And we have D1 and D2. So that's it. We have the European call option formula, and we can calculate everything here. So now we know S naught, that's just the initial stock price. We know K, and we know R. So we have all those bits. Then the D1, that is only a combination of S naught, K, R, and sigma squared, which we know already because we know our stock model, so therefore we know sigma. So we know everything there. And similar for D2, we know all the values there. So we know everything on the right hand side of that, so we can figure out the value of our call option at time 0. But yeah, that's it. So we started off with our simple model, then we seen the risk neutral pricing method, then we redefined our stock. Instead of a simple model, we had a geometric Brownian motion. This had a few implications where we had to do a few different change of probability measures and stuff like that, but eventually we got the formula out, and that is it. Alright, so we have our model. Everything's done, you might think. But you know, with every model, it is actually quite good to consider the assumptions that you've made along the way. You may not realize them, or you may realize them, but we're going to consider them all now. So, for the Black-Scholes model, we have a few assumptions. First, on the asset price. The first one is that we can get a riskless rate of return, called the risk-free rate of interest. Yeah, this assumption is fairly accurate. You can usually get this. It may vary. It might not be constant over time, but in this model we assume it's constant. Then, that your stock price follows the geometric Brownian motion. Another assumption we make on the asset price. This is probably fairly clear. You probably knew this assumption already. Then the stock does not pay a dividend. Yes, so some stocks do pay dividends, a lot of them actually, and this wouldn't work on them. You can change this model slightly to get it, and there's other models which include this, but this normal Black-Scholes does not. Then on the market, we have the most obvious one, no arbitrage opportunity. I probably mentioned it more at the start, but yes, this still is for the continuous model, because we need all our risk neutral measures and we need all these sorts of things that require no arbitrage. Then the ability to borrow and lend any amount at the riskless rate. So yeah, sometimes the borrow and the lend amount might be different, and sometimes you might not be able to do it at any fraction. So we actually do need this. And it was kind of just assumption because we were dealing with kind of mathematics and we just assumed we could have any amount, but in reality this might not hold. Then it's the same with the stock. You can have any sort of fractional amount, and you can also short sell it. That may not be that true. And finally, there is no transaction costs. This is probably not true as well. So it's not a perfect model, but it does work well. Another assumption actually would be that we assume our volatility is constant. That I have not included, but should be there. But yeah, so it's not a perfect model, and you'll actually see models that expand on Black-Scholes, and what they do is they might take away some of these assumptions, or they might change them slightly, and therefore you'll get different models. But the most famous model is the Black-Scholes. It was one of the first, and it has this nice risk neutral thing. But that's it, yeah. Hope you enjoyed.